Hello, everybody, and welcome to the very first episode of the Boise High Rocket Club Rocketry course. This is Hunter speaking, the founder of the Boise High Rocket Club and the current captain. So, throughout this entire course, we're going to be going over a couple of things. We're going to start off from the very bottom and go all the way to the top, talking about how rockets work fundamentally. We're going to be talking about how to design solid rocket motors and maybe even liquid in the future, how to design an aerodynamic rocket body that can reach high altitudes, and then maybe eventually talk about space flight and simulation. So to start us off with this very first episode, we're going to be talking about the fundamentals of rocketry, some of those main governing equations that we always need to keep in mind and understand. So, let's talk about them. So to really get started, we need to make sure you know the prerequisites. The prerequisites for this whole section is mainly going to be, of course, some light physics, so that includes forces, momentum, energy, pressure, etc., and specifically the relation between all three of those, well, four. That's very important. And then also some light calculus, so just basic derivatives and integrals, and differential equations. We'll talk about those a little bit. And then the most important thing, vectors. No vectors. I will have links to videos that can help teach you all of these in the description, and let's move on. Alright, so to get started, I want you to imagine a little block with a mass m, and attached to this block, a ball with a mass dm. It's basically just a little mass, a little distinct, tiny piece of mass dm. Well, these two things are connected together, and they're moving to the left at a velocity v. Therefore, the total momentum of the system, p, will be m plus dm times their velocity, v. Now suppose our object m shoots the object dm out at a velocity ve, an exhaust velocity. The big block m will therefore have a small change in velocity dv added to its current velocity. And since the forces are both equal in magnitude and opposite in direction according to Newton's third law, then the net force in this system is zero. Therefore, momentum is conserved. Knowing that momentum is conserved, we can thus write this equality. The term on the left representing the momentum before the ball was shot off, and the term on the right representing the total momentum of the system after the ball was shot off, making sure to remember that VE and V are vectors and that M and dm are scalars. By simplifying out this equation and crossing out the MVs on each side and moving the dVs to one side and the dMs to the other, we get this. Thus the small change in velocity of the big mass will be in the opposite direction at which the small mass is thrown out. By dividing both sides of the equation by a small time change dt, we can see that the rate at which we are throwing mass out of the rocket over time is directly proportional to the rate at which our velocity will change. Since the small change in velocity over small change in time, dv over tt, is really just acceleration, a, we can use F equals ma to write the thrust force, F, as the negative time derivative of mass, or mass flow rate, times the exhaust velocity. The magnitude of the thrust force then will just be the mass flow rate, which I'll write as m dot now, times the magnitude of the exhaust velocity. I'm going to remove the absolute value bars from here on out. However, remember this is only a scalar equation now. To make it a vector equation, you'll have to multiply it by the unit vector of your force direction. To make this thrust equation complete, we need to add one more term, the pressure term. Since most rocket nozzles composed of some sort of pressurized gas being shot out of it, we need to account for the difference in pressure between that gas and the outside atmosphere. At the exit plane of the nozzle where the exhaust is being shot out, it'll have an exhaust pressure, PE. The surrounding atmosphere will then also have its own pressure, P atmosphere, though in this picture it'll just be P naught. The difference between these pressures will then create a pressure force which will also push against the rocket. This force is found by taking the pressure difference and multiplying it by the area of the exit plane of the nozzle, since, force is just pressure times area. Now that we have our thrust equation, we only have three more things to define: total impulse, specific impulse, and characteristic velocity. The total impulse of a rocket engine is defined as the area under the thrust time curve, expressed in Newton seconds. This basically just gives the total change in momentum the engine can impart onto the rocket. Rocket engines are in fact classed by their total impulse, as the bigger the total impulse, the bigger a rocket it can carry, and the farther it can shoot it. While the total impulse more or less tells you the power of a rocket engine, the specific impulse tells you the efficiency. Measured in seconds, the specific impulse is formally defined as the total impulse divided by the weight of the propellant, which is just given by the propellant mass times the gravitational acceleration, 9.8 meters per second squared. It can also be written as the thrust force F divided by the mass flow rate times g. As an example, by taking the thrust forces and the mass flow rates of the Space Shuttle SRBs and the liquid rocket engines, we find that the SRBs have a specific impulse of about 242 seconds, whereas the actual main engines have about 369, showing that the liquid rocket engines are far more efficient. Lastly, we have the characteristic velocity, which is essentially just a measure of the combustion efficiency of your rocket engine. Characteristic velocity is denoted by C star and is written as the chamber pressure in pascals times the throat area in meters per second and divided by the mass flow rate in kilograms per second. Alright, and that concludes this section on the fundamentals of rocket science. I'll probably have an example problem in the description or maybe the comments, I don't know. And we'll come back to talk about nozzle theory in the next one.